So because I think the topic of threads is going to be useful for you, what I'm planning to do is, in addition to this lecture, maybe later in the semester, I'll try this to be sooner than later, we're going to do also an exercise on threads. Okay, so I will show you how you can create threads, how you can run multiple programs at the same time using threads, and also one very powerful tool is how you can use pool of threads, okay, which is something that will really make your code, and if you build an application, it will make it way more responsive. So we're going to talk about those things today. Okay, so first of all, before starting, does anyone know what are threads? What would we use them for? Any ideas? I'm sure you have some knowledge on that. Okay, yeah. So yeah, I mean, all of you, if I combine all the answers, we're actually going to get what threads are. So threads are instructions, so just a program that is running in parallel with another program. Okay, so let's say if you're having a Word document that you're writing essay inside this document, there you want maybe to perform two tasks at the same time. One of them is the ability to write something, and maybe another thing is to do grammar check meanwhile. Okay, so if you just write a normal program, the program go line by line, right? So you execute line 1, after that line 2, 3, 4, and so on. In threads, this is not like this. You can execute multiple files or different lines of programs at the same time. This is the basic idea. How that helps? Obviously, it makes you perform more tasks at the same time, and you can also utilize your computer resources better. Okay? Alright, so this is pretty much what you already said. Okay, so we can execute multiple tasks at the same time. Okay, and most of the applications these days in the operating systems are running into threads. Okay, so now what is the difference then between a process and a thread? So we might say, okay, inside our computer we can run multiple processes at the same time. So why we cannot just run two processes that are doing, so one process is doing the writing, the other one is doing the grammar check. Okay, they can work together. So why do we even need threads? So what is the difference here? What you can see actually is a single thread process and a multi-thread process, right? Okay, so obviously we can create two processes, they can run at the same time, do two different functions at the same time. However, creating a process is a heavy work. You need to allocate space, you need to load specific code file, right? You also need to load specific data to take specific space of your hard disk, let's say, and of your memory. So this might be too heavy work for the computer, especially knowing that we run thousands of programs at the same time. So instead, what we can do is we can share the code, we can share the data, and we can share the files. Okay, we can have this information accessible from multiple threads, and multiple threads can run in the same process, right? So instead of creating two processes, we can share the code, the data, and the files, and we can create a different register in the CPU for each thread while running on the same process. So you probably heard the words multi-threading and multi-processing. Okay, with programming you can do both. In Java you can do that, yes, true. You can do it also on C, you can do it on Python as well. Actually, today I'm gonna give you some examples on C and Java for threading, and in the practical exercise we're also going to do threading in Python. Okay, so you can see how it differs into the different programming languages. It is always pretty straightforward. but this is the idea. So you can see that doing threads, we have some motivation about it, right? We want to save some space, we want to save resources, we want our operating system to be more optimized and have less processes and more threads. So here is what happens when you create a thread. So we're creating a thread, right? And after a thread, for example, let's say we have a process where this process wants to allocate some task to a thread. So the process can create multiple threads at the same time and just wait for their finishing, or it can create multiple threads at the same time and then resume its task. Okay, so both ways are possible. Normally the process keeps track on the location of the threads, and this is because we want to be able to also stop the threads. So if we want to stop them, we need to also know where they are. Okay, so why do we do threads? Here are some benefits. Okay, so for example, maybe you want to create a computer program that you want to continue execute if some portion of the program is blocked. Okay, so for example, if I create an application that does some task for a very long time, I will see the application as frozen. For example, I'm sure that sometimes when you open some application, something happens and the application is just frozen and nothing happens on it, right? On your device. Well, this is because you're running some process that didn't finish, okay? And until this process finish, your application is not going to be responsive, okay? So when you have threads, you put in a thread the task that has to be performed and the application is still available. You can still access it, okay? And I will try to demonstrate this to you next time when we talk about threads and when we do the practical exercise. Okay. The other benefit is obviously when we share resources. Okay. So threads are sharing the resources of the process, which means that first of all, the memory is shared more easily, and second of all, we don't need to allocate new memory for every next process we create. Okay. Then economy, obviously it is cheaper because we use less computer space. Okay, and it is also more scalable, and I will show you later in the presentation, especially with the multi-processor or the multi-core systems, how you can really use those to benefit from threads. So before jumping into that, we need to make sure that we can distinguish between concurrency and parallelism. Okay, so in operating system, we can do both. We can run things concurrently or we can run things in parallel. Okay, concurrently means that we're able to set to run more than one tasks at the same time. Okay, so for example, imagine a system that is only of a single core. Okay, obviously on a single core system, you cannot run things in parallel because you have only one engine, right? To run all the tasks. So what the processor is going to do, it will do some portion of a task, then it will do some portion of another task, so it will be able to deal with multiple tasks at the same time, okay? But they will still, each portion will run one after another, so they're not gonna run in parallel. They're not gonna run, they will never run together, okay? We're going to do a lot of swapping, right? So you can see this on the figure here. We run task 1, then we run some portion of task 2, task 3, task 4. So the things will happen so quickly that you will think, okay, I'm running like so many processes at the same time. But no, instead of this, the CPU is swapping between those tasks, and this is called concurrency. We're still able to run many tasks at the same time. So if you want to do tasks and run them in parallel, then for this you will need a multi-core system, where one core is doing some specific tasks, while the other core is doing other types of tasks. And those can be done at the same time. Okay, so this is the main difference. Of course, a system can be at the same time concurrent and parallel, right? So every core is capable of doing multiple tasks, okay, but they can run in parallel. This is why the more cores you have, the more work you can do. Okay. So because of the fact that we're having multi-core systems that allows us to run things in parallel, then we need to think of a completely different way to create programs. Okay, so if we're able to run programs in parallel, we want to create programs that can support this thing, right? So the programmers have to start thinking, okay, I want to create a library that is able to do that automatically, so I don't need to do everything from scratch. Just like you said about Java, right? So in the Java, you can use threads library. Actually, it is called the runnable library, is the base library in Java with which you can run threads. And you just need to call it, and then you can create threads, and you can run things at the same time. With Python, you can use threading to create threads, okay, or pool of threads. For example, in Python, you use threading, then you call two different functions as thread1 and thread2, and then you can start them at the same time. So those libraries would never be available if we didn't have this way of thinking, how to run things in parallel. So obviously, when we need to do that, we need to take measures about some things. Okay, the first thing is we need to identify tasks that are worth it to be run in parallel, as we gave the example for the Word document editing, right? At the same time, I think I gave this example already. Let's say if we go to a browser and we open multiple tabs, we also want those processes. Let's say we can have one process there and run the tabs as multiple threads. Hello. This can also be applied to when you open a web page. When you open a web page, there are multiple threads. One of them is loading the text, another one is loading some of the pictures, so the page can be really displayed in front of you at the same time. You know, for example, in Google Chrome, while the page is loading, if you click the X on the site near the bar when you write the name of the website, you stop the loading of those threads, and then the page is not going to be loaded completely. Okay? Okay. So also when we talk about threads, and this is very important, we need to really think about the data splitting. So let's say if I have a list of numbers that I want to sum, maybe I want to have one thread summing the numbers from 0 until the middle of the list, and then another thread summing from the middle until the end, right? So I need to really think how to divide the data between those threads so they can perform an optimal work, and so they can also give the correct result, right? Okay, so in the multi-core systems, we have normally two types of parallelism, and those are data parallelism, and then we have a task parallelism. The process or the threads that can run in parallel based on data is just what I described. So let's say you have a piece of data and you allocate different portion of this data to the different threads, okay? And then they can do their own calculations, and in the end they can, let's say, sum the answers. They can sum the answers and give you the result, okay? So this is data parallelism. We have multiple threads doing the same thing, and after that you sum the result. In the task parallelism, the threads are doing different tasks, okay? So let's say one thread is calculating something, another thread is calculating something else. For example, when we load the web page, one thread is loading the text, another one is loading the pictures, and so on. This is task parallelism. Okay. So you remember from what we spoke in the previous lectures that normally when you're dealing with operating systems, you have two modes, right? What were those modes? Yeah.
User.
Yeah. And the other one? Kernel mode. Yeah. So normally you have, yeah. I mean, yeah. Okay. It's not exactly. So since you have two modes, obviously you're going to have two types of threads, one type for each mode. In operating systems, you need to be able to make a good communication between the threads in user mode and the threads in kernel mode, just like with the processes. So you can call for example, a process in user mode, and then this process might want to do a system call, so you switch to kernel mode for a second or two, and then you go back to user mode. And a similar thing it is with threads, okay? So you have user threads, okay, that are applicable for the user level programs, and then when you need to do something in the system, you need to connect the user thread with a kernel thread. For example, if you want to read or write to a file. Okay? So there are a few different types of how we connect user threads with kernel threads. Okay? So let's look at those types. Those are many-to-one, one-to-one, and many-to-many. Okay? So first of all, we're going to look how many user threads are connected with one kernel thread. Okay, so you can see this is the first option. So let's say your operating system can create a process. Okay, this process can have multiple threads. Okay, and if you use many-to-one mode, this means that every time when a thread wants to talk to the kernel, it needs to wait for other threads that are also talking to the kernel. Okay, so let's say we have two threads. Both threads, they want to write into a file, or both threads want to create a file, right? So what's happening when thread number one wants to create a file? Thread number two needs to wait for it, okay, because thread number one is making busy the kernel thread running on the background. So we need to have some waiting. Now, obviously, this is going to save the kernel resources, but on the other side, we're a little bit slower because we can, on the user side, we were thinking, okay, we have multiple threads, but if all of those threads want to do something in the kernel level, then we're just having a single thread, right? We do everything step by step. We don't do things in parallel in this case. So instead, we can use another approach, which is one-to-one. This means if we have a process with 5 user threads and they want to create a file at the same time, each of those calls a different kernel thread. Okay? So this means we're taking more resources on the operating system, but we're this time obviously way faster. This is an actual threading because actually everything even on kernel level is happening at the same time. Okay? What is the disadvantage? Obviously, if you have set that every user thread can create a kernel thread, you can easily overwhelm the kernel. You just need about a million files, a million threads that want to create files, okay? And you're gonna create multiple kernel threads, and it is possible that you crash the operating system, right? So this is obviously the negative side. Can we have a some solution that is in the middle? Obviously, this is going to be the third type. And this is many-to-many. So into the many-to-many architecture, you can have map many kernel threads to many user threads, okay? They can be the same, or the kernel threads can also be less. So let's say I'm going to define now use maximum of 10 kernel threads, no matter how many user threads they are. So in that way, I am doing the things way faster because I have more kernel threads, but also at the same time I have some limit. I have the limit of 10 kernel threads, and this means I cannot overwhelm my operating system. So let's say if there are way more user threads, so let's say I have 20 user threads and 10 kernel threads, once I fill all the kernel threads, then the other tasks from the user side just need to wait until we have another thread available. So this is sort of a middle ground where you can actually have both advantages of the first two models. Okay, and actually this is some version of many-to-many. While you're doing the many-to-many approach, you can also set a piece of code that there are some user threads that for sure for them we need a separate kernel thread. Maybe just because they're very important, or this is how we did our design. So when the kernel receives a call from a specific user thread with higher importance, they can create additional thread for it. Okay? All right, so now we're going to talk about threading libraries, okay? Or those are software libraries in different programming languages with which we can actually create threads. So in most of the cases, they're implemented as an API, so those APIs are available in Windows, in Linux, and so on, okay? And they can be in the user space or embedded into the operating system. All right. So as you can see, the first library that we're going to talk about is the path reads or pthreads. I think it's more accurate to say. So in pthreads, I will show you a few examples. Okay, you are going to see example in Linux as well, in Windows as well, on how we can use the API in order to be able to create threads. Okay, so let's actually go. I think I have a code that I can show you. So this is an example of using the pthreads in order to create two threads. Okay, so you can see that in this program. So obviously this is a C code, right? We can all recognize it. So what is happening here? First of all, we can, so obviously what's happening in the main, obviously the code is going to start from here, right? Because here is the main function, okay? So let's look on what is outside the main, okay? So the first thing that we can notice is this variable right here, the sum variable, okay? So in C, you probably know that when we define a variable outside the scope of a function, this variable is global by default, okay? So this means that this variable can be updated from different functions, okay? And they can all change its value, okay? So it is global for everything, okay? And here, as you can see, okay, so here we just see the definition, and here is the implementation of a function that is called runner. Okay, so this is a function that sums all the non-negative integers. Okay, so how we can run this runner function as a thread? Using, so we want to run this runner function, and we want this runner function obviously to increase the global parameter that is called sum. Okay, so how we do that? So first of all, we're going to use the pthreads, okay, and we're going to create a thread identifier, okay. Then we're gonna create a variable for the thread attributes, okay. And after that, here is where we're going to run the thread, okay. So right here, we're going to create a new thread using the pthread create, okay. And we're going to provide the ID that we just set for the thread, okay. So when you create a thread, this doesn't mean that the thread started running, okay. So in order for the code to define the wait for the execution of the thread, we need to specify always the join keyword. So actually, let me show something. So normally, firstly, you need to create a thread. This is for every programming language, okay? So the first step is always create, okay? Then we have start, and then we have join, okay? So right here, since we already created the ID of the thread, we can call that this is pretty much the creation of the thread attributes, okay? When we call this function pthread create, we're actually creating the thread. So in this case, for this particular example, the create and the start are pretty much happening at the same time, okay? So we create a thread and then we start it. You will see that in Java we explicitly specify when the thread is created and when it is started. So created means that the thread exists but it's not running yet. Start means the thread starts working, okay? And join, it's a very important portion. This is a line of code where we wait until the thread finishes, okay? So in this case, you can see that after we create the thread, the main thread, which is here, okay, so this main function, you can also imagine it as a thread, okay? So this is the program here working, okay? We create a thread inside, and now here we start waiting until the thread is completed, okay? So once the thread is completed, and it sums all the numbers that we pass to it, and it finishes the job, then we're going to simply print the result from the main thread. So in this case, what's happening is you can see the main thread doesn't continue execution until the child thread completes, okay? So it's very important the join keyword, but in our practical exercise, you are really going to see how those different elements are actually working, okay? So if, let's say, I want to create 5 different threads, okay, I can create them with this keyword. I can start all of them, so the code is not going to stop. I can do start thread 1, start thread 2, start thread 3, okay, they can all start, okay. And after that, we're just going to write the name of every thread, okay, let's say t1 dot join, okay, then t2 dot join, and like this. So here we're just going to wait until all the threads complete, okay. So this is an example with the pthreads library, and here is an example for, let's say, if you want to run an array of threads at the same time, okay. So with the pthreads library, you can do that as pthreads workers. Then you can specify the number of threads, okay. And after that, in this for loop, we are just joining all the threads. So you can imagine this as writing thread 1 join, thread 2 join. So here in this for loop, we're just waiting until all of the 10 threads complete. That way, you can see it is way more shorter. You don't need to create every thread independently and then join every thread independently. Okay? All right. So this is also a C code, but this is how it is implemented, for example, on Windows. Okay, so this is a real version of how you would actually run threads in the Windows. Okay? Questions? Okay. So it is very similar actually. So here we have our function that is called summation. Okay. Then we globally define our sum variable. And here again you have the main function, which is doing exactly the same thing. Okay. Here we're just using a different library which is specific for Windows. Okay. So you can see that right here. Okay, we're creating the thread with this function, so obviously provide an ID, etc., etc. Okay. After that, we wait for the thread to finish. So this is the version of the join inside Windows. So here we're waiting. Okay, and finally here we close the program or close the thread once the thread completes. Okay, this is how it's done in Windows, and as you can see, in the end we again print the result of the summation. Okay, so it is pretty simple code. Any issues understanding it? If you have any questions, I can clarify even more. But I think it's very straightforward, right? All right, so a last example, and this is with Java, how threads are built in Java. So here, as I said, since Java is object-oriented language, so there everything is in classes and objects. Okay, so here we can create threads with the runnable function. Okay, and here's how it works. Okay, so here instead of defining the sum variable globally, obviously we cannot do that. We need to create it as part of a class, right? So here we can have one class that is called sum. Okay, and then the summation integer can be an integer as part of this class. Okay, so then we can create here the class summation that implements runnable. Okay, and here we're going to do the calculation. Okay, and right here inside the driver, obviously public static void main, which is where our code starts in Java. Okay, here we're going to create a new sum object. Okay, so we're going to create a new object of type sum, and then here we can use the thread library to create a new thread. So here you can see we use the start keyword in order to start the thread. So the thread will start now updating the object. Okay, so it will run this function and it will update this sum object right here. Okay, so what's happening is, firstly, we access this variable by using the class. After that, we run a new thread from the summation class, passing this variable. Okay, we go here and then we start updating our sum. So we start the thread, and then here we're waiting until the thread completes. Okay, once it completes, again we can print wherever we like. So this is how it's done in Java. Now, the examples that I just showed you, they were examples of explicit threading. Explicit threading means that we create the threads by ourselves. But sometimes we can also separate our code from the threads creation. And this is something very powerful. Okay, because if you imagine in the operating systems, they can be thousands and thousands of threads. Okay, so what we want is when we want to run our code, automatically a thread is allocated to our code, and we don't even need to create thread within our code, right? So to do that, we can use a few methodologies. I would say the most popular of those are the thread pools and the OpenMP. Okay, and I will make sure that once we do our practical exercise, I show you how thread pools are used, which is something very powerful, as I said. I can give you an example. Recently, I was building an application where I wanted to connect with ChatGPT multiple times. Okay, maybe let's say 5,000 times I wanted to connect every second in order to my program to be able to obtain a lot of data very quickly. So I don't want to wait 5,000 seconds. I want to wait just 1 second. Okay, so if I want to do that, I either have to create a for loop from 1 to 5,000 and to create multiple threads, or I just need to do 5,000 times, start, execute, and so on. Instead, I can use pools and I can define, okay, create me a pool of 50 threads in order to run those 5,000 tasks. And then what is going to happen? The program will take 50 of my tasks, it will push them into the threads, okay, so they'll start executing. Once one of them completes, it will be replaced with the next task, okay. That way I can define separately how many threads I want and how many tasks I want to be completed, okay. It is very easy to implement. But yeah, OpenMP is a little bit lower level, but we're gonna get there. So let's first go with the pools. Okay, so as I described, pools are very good and they are faster than creating a new thread every time. Okay, you can easily allocate tasks to threads using pools. Okay, and once a task is performed and the thread is available, you can then reuse that thread. You don't need to close it and run another task there. Okay, you can also do and add some period. Okay, so let's say if thread 1 doesn't complete within certain amount of time, then you want to close the thread, close the task, and then run another task inside that thread. Okay, so this is an example of a Windows API with which you can create pools. Okay, I will show you also how this is done in Python. It is the same simple, it is just a single function, and you need to specify the function that wants to execute, the amount of tasks, and the amount of threads. Okay, so the next thing we're going to talk about is the OpenMP, which is, you can imagine it as a library that identifies parallel regions in your system. Okay, so let's say if you're running a system of 4 cores, it will simply identify how many cores you have and it will try to optimize them. Okay, so let's say in your code you have a task like right here. Let's say you want to run this block of code, right? And this block of code might take, let's say, 10 seconds normally. If you use the OpenMP and you add this marker right here, what will happen is that this block of code will get divided into 4 if you have 4 cores, and it will execute on every core. Okay, so on 4 core systems, obviously your task will be performed 4 times faster. Okay, so you can see that right here for this task, this for loop, let's say, you can also use the OpenMP like this. Okay, so you write a statement and then you write the for loop. So this for loop then will run on all the 4 cores and this will improve the time. Okay, Any questions so far? Okay. Have any one of you so far used threads in your work, guys? At any point? You used threads before? Oh, okay. All right. Well, I guess that's not bad, because this means that next time when we do our practical exercise, you're going to actually learn something new. Actually, even if you currently are working on application or on some code, you can directly implement what we're going to do into your already existing code. Okay, so that way it is able to actually run faster. Okay, so until the next lecture, you can think of some task in programming that takes time, and we can resolve this task way faster using threads. Okay, I think we will help here.
I have an application app that's coming, just like Facebook.
You have a Facebook app, something like this?
Threads, yes.
Is it there?
No, no.
Ah, okay.
Normally the name, like, Threads.
Oh, it is called threads. Yeah, it is true. Yes. I thought you have some like Facebook clone or something like this that you want to try it on. Okay, got it, got it. Yes, yes. So this is where it comes from, right? Yes.
I don't know, it's a very cheap on the platform.
Okay. So I will answer your question in two ways. I will answer it how you can calculate it, like on theory, and how programmers are doing it in practice. For example, in your case, what happened? What I think happened. So normally, let's say in your case, they run 500 threads and they told you, okay, we cannot do more threads. Maybe, I suspect, they tried to run, let's say, 6, 7, 800 threads, and then the system started throttling. Okay, so this means that after, let's say, 500 in your case, there are too many threads working at the same time, so your hardware cannot keep up. Okay, I know it because I've also had a similar problem just for the application that I just mentioned that I built. And let's say I decided, okay, I want, for example, 50 threads. I use specifically the number 50 because, let's say, if I do 100, then the system starts throttling, which means that it just stucks, okay, because there is you're taking too much. So let's say you create a process. Obviously, a process cannot accommodate as many threads as possible, right? Process is limited on how much hardware, how much memory you have available, right? So each thread, if you create 500, each is going to take space, okay? So in this case, maybe 500 was just the maximum before the space is no longer available, and this is why they told you we can do only 500. This is in practice. Okay, you can try, you see that it starts throttling, and then you just reduce the number of threads. In theory, of course, you can calculate that, right? You can see how much space each thread is going to take and how much time, okay? And based on this, if you know the memory that you have available, you can calculate how many threads you can actually have in your system. You can also, for example, let's say run the program, run for one thread, and you can monitor, for example, on the task manager, this program, how much space it takes. Then you can multiply this by the number of threads you want to create, and this is how you're going to find out. Make sense? Yeah. But yeah, this is a live example that I can think of. Also, another reason might be, for example, this traffic that they were running, was it on a web application? Maybe they didn't want to buy more hardware from the cloud or something like this.
No, they didn't have this. And the cloud stuff. They say that the cloud in the data, right? So,
Okay, in the data center.
Yeah.
So they need to the data center. Did your company own the servers, or it was using a cloud of a third party?
no, they actually own the hardware.
Okay.
Yeah, so every time they needed to upgrade, say increase the number of TPS, they had to buy extra hardware.
Exactly. So maybe they just thought, okay, if we're gonna increase the size, maybe we need to buy more hardware, and for this reason we cannot, let's say, increase the number of threads for this particular application. Probably, I don't know, maybe a different reason, but this sounds the most possible for me. All right, so this is how we can use OpenMP. Okay. All right, so another interesting thing about threads is, for example, let's think about it. If we have, let's say, a process that wants to create a thread, there are two ways, right? So the first way is to simply allocate a new space within the process and then run some code into that space. Another way is to clone another thread, right? So if we clone another thread and this thread is running other threads, are we also cloning the other threads as well or not? Right? This is a good question. So obviously, if we clone the other threads, we should know some information about them. How many space they take? Okay, are they going to overwhelm our operating system? So really, both of the ways are available in today's operating system. Okay, you can either, for example, when you do fork in Linux, okay, you can either just create a new thread, right, copying the original code of some other thread, or you can fork and create a new thread and copy the code of the previous thread, and also all the threads run into the one that we copied. Okay, so now, so when we're dealing with threads, and when we want to create a new one, we want to assess a process, we're always dealing with signals, right? So signal means that we're getting some information. Let's say when we run the fork command, we're sending a signal that we want to create a new thread, okay? Also, when we run a thread, if the code of the thread fails, a signal is raised that there is some change of state, right? So we should do something when there's a signal. A signal can be the thread failed. A signal can be, okay, from this thread I want to open another one. A signal can be many things. Can be, for example, okay, I want to allocate more resources to this particular thread, or I want to cancel a thread. Okay, so there are two types of signals, synchronous and asynchronous. The synchronous ones are always coming to the source. For example, if a thread receives an error, okay, then a signal comes back to the thread saying that this thread should be cancelled, right? And also when we create a thread and a signal is raised, we are having two types of signal handlers. We have a default one and we have a custom one that is non-default. So in programming, we need to be prepared in every case scenario. Okay, so we need to have some small bit of code in the trace library that defines what would happen if there is an error. Okay, and we can say that this is the default handler. So in every thread library, there is a default handlers. Any event that occurs, okay, it is handled based on this code. Now, we can also write non-default handlers, okay, or user-defined handlers. This means, for example, if we expect the thread to fail, and this is our intent, we can set a code that says, okay, try this thread, okay, accept, and if this thread fails, obviously we want some other tasks to appear. I can give you an example. Let's say we have multiple threads that are searching into a database. So we have a database of millions and millions of entries, and we really want to search them quickly. So I'm gonna create 500 threads. Once one of the threads finds what we are looking for, do we need the rest 499? No, we don't need them. Okay, so we can set some handler that is saying, for example, when one of the threads finds something, okay, send the signal to the rest, so the rest can stop execution, okay, or can be cancelled. And this can be an example of user-defined handler. Okay. So when we deliver the signal, they are really those 4 scenarios. I left them as a reference, so you know the how we're handling them. Okay, so the first type is, for example, we deliver the signal to the thread in which the signal applies. Okay, so obviously a thread gets an error and the signal comes back to the thread. Okay, we can deliver the signal to every thread in the process, and this is the example in the searching of the database. Okay, so one thread finds the information, and then we deliver the signal to all the threads, and then all the threads are cancelled. Okay, we can also deliver the signal to certain threads. So let's say if we have a process that half of the threads are searching something in the database, we can know their IDs, okay, and then if one finds something, we can deliver the signal only to those threads, but we don't need to cancel all the threads in the process, right? So you can imagine a process. Let's say, again, I'll give you an example with Microsoft Word. So we have one thread for writing the code, one thread for the grammar, and we have 5 threads for searching a keyword. Okay, so when we find the keyword, we want to cancel all the 5 threads that are searching the keyword, but we obviously don't want to cancel the ones for the grammar and the ones for writing the text. Okay. Okay, and the final one is to assign a specific thread to receive all the signals in the process. Okay, so let's say we can have one thread that no matter what other thread creates a signal, okay, it all goes to one thread, and this thread is making the decisions, right? It might be a thread that is raising some flag or alarm. Okay, so let's say you have a system that is monitoring for some tasks, and if one of those tasks happen, then you want to raise an alarm. That way, if a task happen, a signal will be sent to the main thread, and then the main thread will have the code implementation for a specific signal. Okay. Okay, and this is the same when we're canceling threads, right? So we can have asynchronous cancellation. Okay, means that we're terminating a specific thread, okay, immediately. So this means, for example, let's say you're having a process and you want to kill it. In Linux, you can use the kill keyword. So you can do kill -9 and the pit of the process. This will cancel all the threads and it will kill the process. Okay, so this is asynchronous cancellation. It kills all the threads immediately. We can also have deferred cancellation. So the reason we have that is sometimes if a thread is working and we want to terminate it, we don't know at what stage of its work the thread was. For example, you're running a code, okay, and the code is doing calculations, and just before the code uploads those calculations to the database, you kill the process. So even though the calculations were done, it will never reach the database, unfortunately. Now, if we choose the deferred cancellation, we're going to wait for some time, okay, and then we're going to cancel the thread. So we'll have the opportunity for uploading this data actually to the database. So if we use this option, this means that we're going to call the cancel and we're going to periodically check if the thread in fact has been cancelled. This is in the same way, let's say on your computer, if you try to close a program, sometimes it doesn't close because there are things happening in the background, threads are running. So you're doing deferred cancellation and this means that you're waiting for some tasks in the program to complete. If you terminate the program, all of the threads inside are going to get cancelled immediately. So some of your work might not be saved if the program tries to save some information, right? All right, and yeah, so you can see here, this is a code example, okay, of how you can create a thread right here. Okay, so we use the thread ID, okay, you can define how many workers you want. And finally, here you can, for example, this is in pthreads, you can simply use the pthread underscore cancel and then use the thread ID in order to close the program or close the thread in this case. Okay, and this is simply a table with the different states. So for example, you can enable thread cancellation, okay, or you can disable it. So if it is enabled, it can be either deferred or asynchronous. If it is disabled, obviously we cannot do neither of those cancellations. And here you can see the pthread library again, that is used to wait for a cancellation point. Okay, so I showed you on the previous slide that, for example, here, okay, we're explicitly canceling the thread, while here with the pthread test cancel, we're testing if we can currently cancel the thread. For example, if the thread is alive, but there are no tasks and nothing is getting processed, this function will check and eventually will actually cancel the thread. Okay? Any questions so far? Okay. Who's got a topic for the threads? Have you looked at the list?
It's Mahesh.
Him?
He's spent that.
Oh, he just went out? Okay. Okay. Yeah, so he will have some fun. But it's a good topic. It's a good topic to present, I think. Okay. So now, since we spoke about threads, now I think it is also important to talk about how are we using the storages when we use threads, right? So normally the threads, they share the storage of the process. Okay, since the thread is part of a process, when we create a process, okay, with multiple threads inside, every thread is going to take a portion from this process, okay? And thread local storage is known as TLS, okay? And this is the amount of storage that each thread will have, okay? So it is useful to set the storage, especially if we don't have control over what code it is executed in the thread. So for example, if you create a pool of threads and then you want to run different tasks on those threads, you might not know how much memory each task will require, right? So we run a task inside this thread. So you might want to manually set a large thread local storage, so you can make sure that every code that is executing within the thread has enough space, okay? And also you want to make sure that each thread doesn't also take too much space, so then your CPU starts throttling and your computer is not able to process any more data. Okay, so now we're going to look at two operating system examples. So we're going to look at threads in Linux, and we're going to look at threads in Windows as well. So in Windows, we have a very standard way of implementing threads. So in Windows, we're going to run multiple processes, and each process can have multiple threads, okay? And just as usual, every thread will contain a thread ID. Okay. Then we're gonna have some state related to the processor. So if this thread is being just created, if it's executing, if we are waiting for execution, and so on. Okay. And in Windows, just as we discussed before, we would have user threads and kernel threads at the same time. And the user threads will be able to communicate with the kernel threads based on the ways that we described a little bit earlier. Okay. So every thread will have allocated resources, register set, storage area, and so on. So the primary data structures in Windows for threads are the E thread, K thread, and TEB, which is thread environment block. Okay. So the E thread is normally including a pointer to the process in which the thread belongs. Okay. Normally in the kernel space. Okay. And this is going to be the thread that is running above the kernel, okay, in the user level. Then the key thread is going to be the kernel level thread, okay, and this type of thread is obviously going to take resources from the kernel, and this is the type of thread that is running in the kernel. And the TEB, thread environment block, is obviously all the set of information that a thread has. Okay, thread ID, user mode stack, thread local storage, user space, and so on. Okay, so you can imagine this more of a user level, kernel level. Okay, and this is pretty much making the relation between both. Okay, and you can see how they are connected. So here from the thread you can assess the kernel thread. Okay, and finally here you have the thread identifier, you allocate the storage, and so on. Okay. So in Linux the things are a little bit different there. So in Linux we really don't have the concepts of threads and processes. Okay, so in Linux everything is called task. So when we want to execute some code, we are creating a new task. So we can create a thread using, or we can clone the thread using the clone keyword. We can create a new thread also by using the fork system call. Okay. So there are different flags with which we can clone a thread. Okay. So for example, if you use the clone fs flag, means that we're going to clone a thread and we're going to copy some file system information. Okay, so let's say the information between the thread we cloned and the thread we created is going to be shared. Okay, if you use a clone VM, this would mean that we're going to share some memory space. Okay, we can share signal handlers. Okay, if you use a clone sync hand, right? Okay, so that way we can share actually the signal between the two threads that we clone with each other. Okay, and finally, in the final way, we can share the set of open files. For example, if thread 1 has some particular files that are open, we're going to share them with thread 2. Okay. All right, guys. So you're going to see next time when we're doing our practical exercise that the threads in Python. So since Python is interpreted language, okay, the threads there are going to be created in the same way, no matter whether you use Windows or Linux. Okay, and I think it's really the best way to learn threading, because you're not going to be tied up to your operating system. The same thing is with Java as well, right? So I think it will be a very good exercise. But this is as far as it goes about the theoretical part.